Next, let's take a look at density curves. If you have already taken calculus, you might recognize this picture where you were trying to find the area under a curve. So you estimated by making a bunch of small rectangles, and then you knew how to find the area of the rectangle by doing length times width. And theoretically, what you thought about was what would happen if we made these rectangles more and more narrow so that eventually your area covered up by the rectangles would match the curve closer and closer. That's kind of the same idea that we're thinking about here. If we were to take more and more samples of data and we would have thinner and thinner intervals on our histogram would start to look like a curve rather than a bunch of rectangles. So the curve itself is called a density curve. A couple of things that are important about a density curve is that it is always above the x-axis, and the area underneath the entire curve always equals exactly 1. Just like we discussed measures of center and spread, such as mean, median, standard deviation, just like we discussed them with collecting data and making histograms, they also apply to density curves. In a density curve, the median is the point right in the middle of all of the area, so that you would have 50% of the area below that point and 50% above. The mean is sort of like a balance point. So if you could physically cut out the density curve like out of a piece of wood or something and you tried to balance it on the tip of your finger, that's where the mean would be. And if your data is symmetric, then the median and the mean are going to be in the exact same spot, right in the middle. However, if your data is skewed, whichever way the skew is, that pulls the mean in that direction. So if your data is skewed to the right, that means your median gets pulled to the right, or in other words, your mean gets a little bit larger. If your data is skewed to the left, that means your mean gets pulled to the left or it becomes a little bit smaller. So here are some pictures. The density curve on the left is symmetric, so the median and the mean are in the same location, whereas the density curve on the right is skewed to the right, and that balance point or that mean gets pulled a little bit towards the right. Now, when we move from a distribution of actual data that we've collected to kind of this idealized density curve model, we also change some symbolism to notate that. So you'll remember from earlier in the year, when we had the mean of a distribution of data, we used the symbol X bar to represent that. When we move over to density curves, which is kind of this idealized idea of what the population might look like, we switch to the symbol mu, which is a Greek letter. And similarly, back when we were looking at actual data that we collected and we found the standard deviation, that's where we were using the letter S for standard deviation. When we switch over to a density curve, we switch over to using the Greek letter sigma. One specific density curve that we're going to be looking at a lot is called the normal curve, or the normal distribution. And the normal curve might be wider or narrower based on whether or not the standard deviation is larger or smaller, but it's always symmetrical, it's always unimodal, it's always bell-shaped, and the mean is always right in the center. You can tell where the standard deviation is because it's the point where the concavity changes, or the inflection point. So where it goes from curving downwards to curving upwards. That's where you'll find the value of one standard deviation away from the mean. The notation that we'll use to write this is you'll write an n, and then a parenthesis, and then the mean, and then the standard deviation. So for example, if I wanted to talk about a normal curve that had a mean of 80 and a standard deviation of 6.2, I would use this notation.